Given an m by n binary matrix, mat, return the distance of the nearest zero for each cell. The distance between two adjacent cells is 1. So we're given two examples, and let's focus on the second one. So this is our starting matrix, and then this is the return. How do we get this? Whenever there is a 0 to this matrix, we're just going to add a 0 here. And anywhere there is a 1, we're going to find the closest 0 to it. So for this middle one, the closest 0 can be either up, left, or right. So we're just going to put a 1 here, showing the distance between the nearest 0. And here, we need to move 2 spaces until we find any zeros. So we're going to put a 2 here, and this would be our answer for this example. So these were pretty simple examples. Let's try another one to get a better idea of how to approach this problem. So here we have a 4 by 5 matrix, and let's try to fill this out to get our answer. So let's start with the easy stuff first. We know that on all zeros, we're going to have a 0 as well. What about the ones? For some of these, they're pretty easy. We know that any cell that's right next to a 0 is going to have a distance of 1. So we can fill these out as well. So what comes next? For some of these, I'm not too sure. But I do know that here is going to go 2, 2, 2, 2, 2, 2, and a 2. How do I know this? Let's look at one more example. Suppose now that we had this array, what would our answer be? Well, again, we just have a 0 starting here, and then we put 1s next to it because we know that the 1 is just a cell away. So what about here? We're just going to have a 2, and over here, we're going to have a 3. But how did I know that? It's because I'm basing my answer on our previous answers. So for this one, we knew that it was only 1 cell away from the 0. How did I know the 2 go here? It's because I'm building up my answer. I knew that next to any 1 needs to go with 2 because it's only 1 step away from the 1. And the 3 goes here because it's only 1 step away from the 2. So going back to this problem, what we're going to do is we're just going to keep building up our answer. Anytime we see a 2, we're just going to add a 3 to its adjacent cell, and so on. So finishing up this problem, it's just going to be 3, 3, and 3. We can also validate this by putting our example into a test case and getting the answer. This is what it looks like when it's all split out. But this is the same thing that we came up with. Now, one of the more important parts of this is determining which cell we're going to fill out next. We started off first filling out all the zeros, and then we added all of the cells that were adjacent to the 0. And then after that, we just added all of the cells adjacent to the 1s, and so on and so forth. So the way that we attack this problem is that every time we fill out a cell, we're going to add all of its adjacent cells to a queue. Filling it out in this way is how we know it's going to be the shortest distance to the closest 0. So let's get into the code for this. First, let's make our answer array. We're just going to call it DP. And the reason why we're calling it DP is just, this is going to be dynamic programming. Remember, we're building our answer from the bottom up, and this is just a common dynamic programming technique. So let's just set the DP array to copy.deepCopy.mat. So this will give us the right dimensions of it. And let's initialize this DP array. So we're just going to say for I in range len DP, for j in range len DP 0, if mat I j equals 0. Whenever we find a 0, dp I j is going to equal 0. And we're going to say dp I j equals math.inf. This is just infinity. And this is just going to be our placeholder to say that we haven't determined what value is going to go in this cell. We're also going to need a queue. So let's just say q equals that. And how did we approach our problem? After filling out all of our zeros in our answer array, we look to all the cells that are adjacent to it. So first, let's just fill out our queue. So again, if we detect a 0, we're just going to say q dot append, and then we're just going to put in the coordinates. So we're going to have I, j. So now we're going to say while our queue is not empty, while we still have coordinates that need to be checked, we're going to get that next element. We're going to get that next coordinate. So we're going to say I, j is just going to be q dot pop, and let's get the first element. So we're just going to say pop 0. Current value equals dp I, j, and then we're going to look at all of the elements next to it. So to look to the right, we're going to say if dp I plus 1, this means look to the right. If that value is unassigned, we're just going to assign that value to the right to have the value that it's currently at plus 1. And then once we assign that value, we need to check all of its values to see if it's unassigned. So we're going to add that value to the right into the queue, and we're going to apply the same logic for all of the other directions. And then once our queue is empty, when there's no more unassigned cells that need to be assigned, we're going to return our answer, return DP. So that's it. But we do need to consider the case where we go beyond the dimensions of our matrix. So if we go into like the negative, or we go beyond the length of DP. So let's say something like def is I in bounds I, and if 0 is less than or equal to I, and I is less than the length of mat, turn true, else turn false. Same thing with J. We're going to say this, J, J, J. Why do we need two different ones? It's because this isn't always necessarily going to be a square. We have an m by n, which means these values can be different. And this needs to be mat 0 to account for that. And this is what it will look like after you add it in. I want to point out that if you try running this with this on the other side, so if I ran it like, well, actually, let me just run this real quick. So run, let's change that, hit run. This will work. We can hit submit. This will be accepted. Now, if we try to run this looking like this, it'll crash. And why is that? It's because in Python, there's something called logic short circuiting. We evaluate our statements from left to right. So we're going to evaluate this one before moving to this expression. If our first expression returns false and we have an AND condition, that just means that the rest of the expression we know is going to be false, because so long as we have one false in an AND condition, the rest of it's going to be false. We can just stop evaluating right now and to say this is just going to be false. So we don't actually ever evaluate any of the next values after the first false. And that will prevent any potentially program crashing evaluations. The runtime for this should be m by n, so a linear time solution. And the space for this should also just be m by n, because we're using the DP array to store our answer. And that's it. If you found this video helpful, please like, subscribe. A link to the code will be in the description, and leave a comment on what you think I should be attacking next.